What was there before the Big Bang? Scientists have been trying to answer this question for years, but new findings are giving them surprising information. Brian Cox and other experts have shown that the answer may be a lot trickier and scarier than we thought. Cox says the idea is that the universe wasn't hot and dense before the Big Bang as we always think it was. Instead, it was cold, empty, and growing very quickly. The growth we're seeing now is called inflation, and it made the universe what it is today. However, inflation didn't happen everywhere. It stopped in some places, which is what we now call the Big Bang. But it kept going in other places. This idea, called the inflationary multiverse, suggests that our world is only one of many. This perspective sees the universe as a fractal, with an endless number of Big Bangs occurring in different parts of space and time. Each of these areas becomes its own world, and ours is just a small part of a much larger cosmic landscape. But what is inflation and why did science find it so strange? Before the Big Bang, space grew very quickly in a process called inflation. This was caused by a strange kind of energy. At this point in time, space expanded rapidly, making the universe appear flat and even by smoothing out any irregularities. Then, the energy that caused the expansion was released, heating up space and creating the particles that make up everything around us. Previously, scientists thought the Big Bang, a sudden burst of energy, marked the start of everything. Now we know it was just one chapter in the universe's history. This revelation raises new questions. What existed before inflation? Why does the universe continue to expand? The universe is never truly empty. The concept of absolute nothingness doesn't hold in space because of its vastness. Even if all energy were removed, space would still contain quantum fields, the building blocks of reality. These fields ensure that something always remains, even in a vacuum. This is why true nothingness cannot exist, as quantum fields continually generate radiation, even in the absence of particles or energy. Could there have been nothing before the universe? According to current knowledge, space retains some energy even when it is empty. This zero-point energy is the closest concept we have to nothingness, but it still represents the lowest amount of energy present everywhere. As the universe grows, it changes. Space expansion pulls galaxies farther apart, cooling the universe as a whole. After the Big Bang, the universe was hot and dense. Over time, it expanded, becoming larger, colder, and less dense. The light from distant galaxies stretches as space grows, causing redshift, where the light elongates as galaxies move away. This stretching reduces energy and temperature, explaining why the universe is much colder now than at its inception. Even if all matter and energy were removed, empty space would remain, governed by the laws of physics and filled with quantum fields. Dark energy, a mysterious force, accelerates the expansion of the universe. This expansion continues even in the absence of particles or radiation. Inflation played a crucial role in shaping the universe's history. Before inflation, a potent form of energy caused space to expand at unimaginable speeds, smoothing out early irregularities. This process created the flat, even universe we observe today. However, inflation also introduces new questions. Where did it begin? If it persisted in some areas and triggered endless Big Bangs, what role does inflation play in our understanding of the universe? To address these questions, scientists examine three interconnected ideas: the hot Big Bang, cosmic inflation, and the concept of an ultimate beginning. In the early 20th century, astronomers like Edwin Hubble observed galaxies moving away from us, leading to the idea of an expanding universe. This suggested that the universe was smaller and denser in the past, culminating in the concept of the Big Bang, a moment when all matter and radiation were compressed into a single point with infinite density and temperature. While the Big Bang theory explains much, it has limitations. For instance, the horizon problem arises because parts of the universe that never interact share similar properties, suggesting a prior connection. Additionally, the flatness problem questions how the universe maintains its perfect balance between expansion and gravity. Inflation addresses these issues, explaining how rapid expansion smoothed out early irregularities and created the universe's observed traits. Why does the universe have these specific characteristics? Early theories helped explain the Big Bang, but newer ideas like inflation clarify why the universe is so uniform and why expected particles like magnetic monopoles are absent. However, the question of what happened before the Big Bang remains unanswered. In 1980, physicist Alan Guth proposed the theory of inflation, describing an early period of rapid and continuous expansion. Guth suggested that the universe's energy wasn't divided into matter and radiation as it is now. Inflation not only resolved long-standing puzzles but also reshaped our understanding of the universe's origins. This energy, on the other hand, was part of space itself and grew, stretching the universe at an amazing speed. Three main problems are fixed by inflation. The horizon problem asks why the universe seems to have such a uniform temperature and density when different parts of it haven't had time to communicate with each other since the Big Bang. According to inflation, everything was once linked in a small, dense state before it quickly spread out, which explains why things are so similar now. The flatness problem arises because inflation blew up the universe so much that any original curvature is no longer there, making the universe look amazingly flat. Regarding the monopole problem, inflation explains why we don't see strange artifacts like magnetic monopoles, which we should see if the world got too hot. Inflation stopped the universe from reaching those extremes so these leftovers didn't form. Inflation not only solves these problems in cosmology but also gives us clues about how objects in space like galaxies came to be. Small quantum changes in the fabric of space were sped up to cosmic levels during inflation. This created the universe with the bumps that would eventually grow into galaxies, clusters, and stars. The cosmic microwave background, CMB, the afterglow of the Big Bang, and the large-scale framework of the universe all show that these early flaws were real. Even though these changes were very small, they were enough to make everything we see today possible. In the 1980s, scientists made very accurate predictions about how these changes would appear in the CMB. Many observations made since then have confirmed those forecasts, making inflation theory even stronger as an explanation for how the universe got started. Before the Big Bang, what happened? Inflation brings up a very important question. If inflation explains what happened before the Big Bang, does that mean the Big Bang wasn't the real start? In the first model of the Big Bang, the universe could be traced back to a singularity, which is a point where the temperature and density are both infinite. But inflation complicates this idea. Since inflation makes space grow at an exponential rate, it would take an infinite amount of time for the universe to reach a state where it has no size, which is what the Big Bang model suggests happened. It's hard to imagine the world starting from a single point because inflation keeps this from happening. We can only see proof from a very short time ago, like the marks left by quantum fluctuations just before inflation caused the Big Bang. Endless inflation makes things even more complicated. In this scenario, inflation never really ends. It stops in some places like our universe but keeps going in others. This creates a multiverse, a collection of many pocket worlds, each with its own Big Bang. This process erases all records of what might have existed before inflation, making it almost impossible to determine how the universe began after that point. Eternal inflation and the many worlds theory are fascinating but do not go back in time. Studies have shown that spacetime, when expanding, cannot go back in time forever. It must have come from a different, perhaps single, state. This indicates that inflation doesn't always provide a clear answer to where everything came from, even though it explains much about the early universe. Other models, like circular or bouncing cosmologies, struggle to explain where the universe originated. These theories suggest that the world goes through cycles of expansion and contraction, but they still can't resolve the issue of a beginning. What does nothing mean? What did the universe come from if it had a start? It's not as simple as it seems to conceptualize nothingness. Quantum fields still exist even in the emptiest parts of space. Even when there are no particles or energy, these fields still move and interact. In other words, the thing closest to nothing is still something, a vacuum full of quantum potential. The vacuum origin hypothesis proposes that the universe could have originated from a quantum fluctuation in this vacuum. This idea has intrigued physicists for a long time. This theory suggests that the universe began as a change in nothing, which created everything we see today. Although it remains a hypothesis, it is a compelling idea that challenges us to rethink what life and nothingness really mean. Quantum fields and virtual particles play a crucial role in this discussion. Space is not the only component of the universe we observe. Quantum field theory posits that energy fields permeate all of space. These fields interact with one another to create everything from atoms to stars. They remain active even at their lowest energy level, known as the vacuum state. Virtual particles, which are temporary particles that appear and vanish instantly, constantly draw energy from the void. These fields and virtual particles are essential to the structure of the universe, but they complicate our understanding of nothingness. Can we truly say the universe was ever empty if it's filled with these fluctuating fields? Dark energy and the universe's expansion are interconnected. The acceleration of the universe's expansion is driven by dark energy, a mysterious force. While early rapid expansion can be attributed to inflation, the current growth is caused by dark energy. Even in the distant future, when all stars have died and matter is dispersed, dark energy will continue to drive the universe's expansion. In other words, the universe has never been truly empty and likely never will be. The growth, radiation, and quantum fields that fill space will persist as long as dark energy remains. Scientists have been exploring the mysteries of the early universe for decades, and inflation theory has fundamentally altered our understanding. However, it has also introduced new questions. What existed before inflation? What triggered its onset? Why does the universe resist the concept of nothingness? While we don't yet have all the answers, the pursuit of knowledge continues. As we delve deeper into the universe and refine our theories, we edge closer to uncovering the origins of everything we observe. Stay tuned for more articles like this one and share your thoughts about these ideas.